NASA's James Webb telescope has proven its unparalleled ability to study the atmosphere of a massive exoplanet more than 1,000 light-years away, realizing a remarkable dream for astronomers. Webb has discovered haze, clouds, and ambiguous water signatures in a single observation using the combined power of its 270 square foot mirror, precision spectrographs, and sensitive detectors. These discoveries were previously thought to be impossible based on previous observations. Webb's near-infrared imager and slitless spectrograph were used to create the transmission spectrum of the hot gas giant WASP-96b, which provides just a small glimpse into the mission's exciting future of exoplanet exploration. Learn more about these amazing discoveries made by the James Webb Space Telescope by watching towards the end of today's episode. A far-off exoplanet's steamy atmosphere is revealed by Webb. The water vapor signature in the atmosphere of a hot, puffy gas giant orbiting a far-off sun-like star has been captured by JWST. It also discovered indications of clouds and haze. The observation, the most thorough of its kind to date, shows off Webb's amazing capacity to study atmospheres thousands of light-years away. Based on small reductions in the brightness of specific colors of light, it indicates the presence of particular gas molecules. The Hubble Space Telescope has studied the atmosphere of many exoplanets over the past 20 years, detecting water for the first time in 2013. However, Webb's quick and more thorough observation represents a significant advancement in the effort to identify potential habitable planets beyond Earth. There are more than 5,000 confirmed exoplanets in the Milky Way, including WASP-96b. It represents a type of gas giant that has no direct counterpart in our solar system and is roughly 1,150 light-years away in the southern sky constellation Phoenix. WASP-96b is significantly puffier than any other planet orbiting our Sun, with a mass less than half that of Jupiter and a diameter 1 or 2 times greater. It is also noticeably hotter, with a temperature of more than 1,000 degrees Fahrenheit. WASP-96b makes one orbit around its Sun-like star every 3.5 Earth days, orbiting so closely to it that it is only 1/9 the distance between Mercury and the Sun. WASP-96b is the perfect target for atmospheric observations due to its large size, quick orbital period, puffy atmosphere, and absence of contaminating light from nearby stars. On June 21st, the WASP-96 system was observed by Webb's near-infrared imagery and slitless spectrograph. The NIRSS observed for 6.4 hours as the planet moved across the star. The end result is a light curve that depicts the overall dimming of starlight during the transit and a transmission spectrum that shows the brightness variation of specific infrared light wavelengths between 0.6 and 2.8 microns. While the transmission spectrum reveals previously undiscovered details of the atmosphere, the light curve confirms properties of the planet that had already been established from other observations, including its existence, size, and orbit. The clear signature of water, the presence of haze, and clouds that, based on earlier observations, were believed not to exist. The starlight that is filtered by a planet's atmosphere as it passes in front of the star is compared to the unfiltered starlight that is observed when the planet is next to the star to create a transmission spectrum. Based on the absorption pattern, the locations, heights, and peaks on the graph, scientists are able to identify and quantify the abundance of important gases in the planet's atmosphere. Atoms and molecules have distinctive patterns of wavelengths that they absorb, similar to how people have distinguishable fingerprints and DNA sequences. WASP-96b's spectrum, which was recorded by Webb's near-infrared imager and slitless spectrograph NIRSS, not only contains the most accurate near-infrared transmission spectrum of an exoplanet atmosphere to date, but it also spans a remarkable variety of wavelengths, including visible red light and a region of the spectrum that has not previously been accessible from other telescopes. Water and other essential molecules like oxygen, methane, and carbon dioxide, which are not immediately apparent in the WASP-96b spectrum but should be detectable in other exoplanets, are particularly sensitive to this portion of the spectrum. Researchers will be able to measure the amount of water vapor in the atmosphere, constrain the abundance of different elements like carbon and oxygen, and estimate the temperature of the atmosphere with depth using the spectrum which Webb is planning to observe. They can use the data to draw conclusions about the planet's overall composition, as well as how, when, and where it formed. The best fit model, represented by the blue line on the graph, accounts for the data, the known characteristics of WASP 96b and its star, as well as the ascribed properties of the atmosphere. Modern Webb design has made it possible for these measurements to have such exceptional clarity and detail. The 270 square foot gold-plated mirror effectively captures infrared light. Its sensitive infrared detectors detect incredibly minute variations in brightness, and its precise spectrographs disperse light into rainbows of thousands of infrared colors. NIRSS can distinguish brightness differences between colors that are a few hundred parts per million apart and color differences that are only a few thousandth of a micron apart. It covers infrared light wavelengths that we have never had access to before, which is exciting. The infrared atmospheres of exoplanets have been studied by other telescopes, but not with the same level of detail, and this is only a small portion of the data, according to Colin, an expert on exoplanets. In addition to Webb's extreme stability, KITT's orbital location around Lagrange 2 and its distance of about 1 million miles from the Earth's atmosphere allow for an uninterrupted view and quick data analysis. Only a glimpse of what Webb will bring to exoplanet research is shown by the incredibly detailed spectrum created by analysing 280 individual spectra simultaneously. Researchers will use spectrography to examine the atmospheres of dozens of exoplanets, ranging in size from small rocky planets to giants that are abundant in gas and ice over the coming years. Exoplanet research and the materials it produces takes up almost a quarter of JWST cycle in one observation. This closest observation demonstrates Webb's capability to describe exoplanet atmospheres, including those planets that may be habitable. The majority of the science, according to Antonella Noda, a JWST scientist who oversees the European Space Agency's office at the Space Telescope Science Institute, will be conducted using spectra. While we often say that a picture is worth 1,000 words, astronomers only consider spectra to be worth 1,000 pictures. And with that, the episode for today comes to a close. We can only hope that the James Webb Space Telescope's enigmatic discoveries continue to surprise us with new information about exoplanets. Please give us a big thumbs up and subscribe to our channel if you enjoyed what you saw. I'll see you at the next.